Welcome. I am pleased to introduce our session today, titled The Pragmatics of Order. This presentation explores the vital intersection of mathematical theory, hardware realities, and the practical implementation of these concepts within the Go standard library. As we can see from the visualization behind me, our focus is on the journey from initial complexity and entropy toward a structured, efficient state. We will analyze how software can be designed to respect both mathematical principles and physical hardware constraints to create robust systems. Thank you for joining me as we delve into these foundational elements of modern programming. In computer science, the core mandate of sorting rests on two absolute conditions that any valid algorithm must satisfy. First, the output must be in monotonic order. As illustrated by Rule 1, this means that for any sequence of elements from x1 to xn, each element must be less than or equal to the one that follows it, establishing a consistent, non-decreasing sequence. Second, we have Rule 2, which states that the output must be a permutation of the input. This ensures that while we rearrange the elements to achieve order, the output retains all original data points without additions or losses. While these principles are simple to state, optimizing the sorting process against the rigid constraints of time and hardware remains one of the most significant and evolving challenges in computer science. When evaluating the performance and behavior of an algorithm, we focus on three fundamental metrics: time complexity, space complexity, and stability. Time complexity quantifies efficiency by measuring the number of operations, such as comparisons and swaps, relative to the size of the input array. In theoretical terms, the average case limit for comparison-based sorting is O of n log n. Space complexity refers to the auxiliary memory required for the algorithm to execute. We define in-place algorithms as those that are highly memory efficient, requiring only O of 1 or O of log n additional space beyond the storage of the data itself. Finally, we assess stability, which is the preservation of the original relative order for elements with equal sorting keys. This is a critical factor when maintaining data integrity across multi-level sorting operations. The necessity of stable sorting becomes clear when we move beyond simple data types like raw integers. While stability is irrelevant when equal elements are indistinguishable, it becomes critical when sorting complex records by multiple keys. A stable sorting algorithm ensures that the relative order of records with equal keys is preserved, meaning previous sorting passes are not destroyed. Looking at the input example, we have a sequence of 4 cards: the Jack of Spades, the 5 of Clubs, the 5 of Hearts, and the 2 of Diamonds. Notice that the 5 of Clubs appears before the 5 of Hearts in the original unsorted list. In the stable output on the left, the cards are sorted by rank, but the relative order of the 2 5s is maintained. The clubs still precede the hearts. This is the desired outcome when we need to maintain a secondary sort order. Conversely, the unstable output on the right shows that the relative positions of the 5s have been swapped. In a real-world scenario, such as sorting a database by last name and then by first name, an unstable sort would lose the organization established in the first pass. Stability provides the predictability required for multi-level data processing. Mathematical analysis dictates that comparison-based sorting algorithms cannot perform better than O of n log n on average. This represents a fundamental theoretical barrier, forcing every algorithm to accept a specific compromise in memory, worst-case performance, or stability. Merge sort achieves the optimal O of n log n speed and is highly valued for its stability, which ensures the relative order of equal elements is preserved. However, its primary trade-off is memory usage, as it requires O of n auxiliary space to operate. Heap sort provides an alternative by maintaining O of n log n speed while being exceptionally memory efficient with O of 1 in-place space complexity. The sacrifice in this case is stability, as heap sort is an unstable algorithm. Finally, quicksort is often preferred for its excellent average case performance of O of n log n and its relatively low O of log n space requirements. Nevertheless, it presents significant risks. It is unstable and carries a dangerous worst-case time complexity of O of n squared when encountering unfavorable data distributions. Quicksort is known for its efficiency, yet it possesses a significant vulnerability: its reliance on pivot selection during the partition operation. In an ideal scenario, as shown on the left, a well-chosen pivot splits the dataset into 2 relatively equal parts. This results in a balanced recursion tree with a logarithmic depth, maintaining an overall time complexity of O of n log n. However, the algorithm encounters a fatal flaw when pivots are chosen poorly. If a pivot consistently falls at the extreme edge of the data, a common occurrence with already sorted or reverse-sorted inputs, the recursion depth degrades from logarithmic to linear. As the visualization on the right illustrates, this transforms the process into a lopsided chain, causing the algorithm to grind to a halt with a worst-case complexity of O of n squared. While Big O notation provides a useful theoretical framework, it relies on the assumption that every memory access costs the same amount of time. Modern hardware, however, functions differently. Moving data across vast distances in main memory is significantly slower than comparing localized neighbors. As we can see in this hierarchy, the L1 and L2 caches provide high-speed access to data situated close to the CPU. When an array is localized within these tiers, the processor can operate at peak efficiency. This physical reality explains why a theoretically slow O of n squared insertion sort often heavily outperforms more complex algorithms on very small arrays. At this scale, the benefits of memory locality and lower constant factors are more impactful than asymptotic complexity. Practical engineering often requires us to move beyond theoretical purity to achieve optimal real-world performance. Modern sorting implementations exemplify this pragmatism by combining multiple strategies into robust hybrids. We typically utilize the asymptotic efficiency of partitioning methods, such as quicksort, to handle massive datasets. To ensure reliability and prevent excessive recursion depth in worst-case scenarios, these systems are designed to fall back to selection-based methods like heap sort. Finally, as we reach the bottom of the recursion stack, where subproblems are small, the algorithm switches to insertion sort. This transition is vital for respecting hardware caches and minimizing overhead for small datasets. The intersection of these three distinct approaches, partitioning, selection, and insertion, is what produces the highly efficient, industry-standard algorithms we rely on today, such as introsort and timsort. In 2021, a significant innovation in sorting algorithms emerged, known as pattern-defeating quicksort, or PDQ sort. Developed by Orson R. L. Peters, this algorithm represents a major breakthrough as it achieves high performance without requiring three-way comparisons. While PDQ sort is never significantly slower than traditional quicksort implementations, it offers dramatic speedups for many input distributions by actively detecting and breaking bad patterns that typically hinder performance. Its most notable achievement is a proper worst-case runtime of ONK for inputs containing k distinct elements, making it exceptionally efficient for datasets with high levels of redundancy. PDQ sort is an adaptive sorting algorithm designed to maintain high performance while avoiding the quadratic worst-case scenarios often encountered in traditional quicksort. It achieves this through a three-step process aimed at detecting and defeating adversarial data patterns. In step 1, known as the fast path, the algorithm looks for slices that are already partitioned or sorted. If such patterns are detected, it leverages a partial insertion sort to complete the task efficiently. Step 2 involves the balance check. During the partitioning process, the algorithm monitors the ratio of the resulting partitions. If it detects significant imbalance, indicating that the pivot selection is failing to divide the data effectively, it decrements a predefined limit. Finally, in step 3, we see the interventions. When the algorithm identifies that it is struggling, it takes corrective action. This includes scrambling the data elements using an XOR shift random generator to break up problematic patterns. If the balance limit is eventually exhausted and reaches 0, the algorithm falls back to heap sort. This multi-layered approach ensures O(n) log n performance in the worst case, while keeping average speeds exceptionally fast. Computer science papers serve as our theoretical blueprints, outlining the conceptual possibilities of what we can build. However, standard libraries represent the true foundations of modern software, turning those theories into stable, production-ready tools. The Go programming language's sort package is a masterclass in this process, taking complex sorting algorithms from academic research and implementing them behind a remarkably elegant and accessible interface. Go completely abstracts the underlying sorting algorithm. If a user-defined collection, such as the slice of person structs shown here, can report its length, compare two indices, and swap them, the Go standard library handles the highly tuned mathematics of the actual sort. To achieve this, you simply implement the three methods defined in the sort interface: len, which returns the number of elements, less, which determines the sorting order, and swap, which exchanges elements at specific positions. This elegant design allows you to sort any data structure efficiently without needing to re-implement complex sorting logic yourself. Go's standard library has recently transitioned its default sorting implementation to utilize PDQ sort, or pattern defeating quicksort. This represents a pragmatic approach to performance, where the engine dynamically evaluates data patterns to choose the most efficient strategy. Without any manual intervention from the developer, the algorithm seamlessly pivots between insertion sort, quicksort, and heap sort. A key part of this logic involves the limit parameter, which is calculated based on the bit length of the input size. This limit defines how many bad pivots are tolerated. If the partition becomes too unbalanced, the system automatically falls back to heap sort to guarantee O of n log n performance. For smaller subproblems, the engine utilizes a max insertion threshold of 12 elements. At this scale, insertion sort is used to maximize CPU cache efficiency and minimize recursive overhead. Furthermore, the inclusion of an XOR shift function allows the engine to scramble adversarial data layouts, protecting the system from worst-case performance traps and ensuring consistent speed across diverse datasets. To ensure stability, Go's sort.stable implementation diverges from the standard quicksort approach, which is fundamentally unstable. Instead, it employs the sim-merge algorithm combined with block swap rotations. While this introduces a slightly higher overhead of O of n log squared n swaps, it provides a critical guarantee of perfect relative order for equal elements. Furthermore, this approach is highly memory efficient, requiring only logarithmic stack space. As illustrated in the diagram, a block swap effectively rotates contiguous segments U and V within a larger sequence. By swapping these blocks, the algorithm can reorder data as necessary while maintaining the internal stability of individual segments and ensuring the surrounding elements, represented here as X and Y, remain unaffected. Sorting is often viewed as a fundamental task that has been mathematically solved, yet it remains a challenge that is constantly evolving in practice. While theoretical notation provides us with rigid limits and a baseline for performance, the reality of modern computing requires a more nuanced approach. We must adapt our methods to the specific physical architecture of computer memory, considering cache hierarchies and data locality to achieve true efficiency. By applying ruthless engineering pragmatism alongside these theoretical foundations, we are able to bridge the gap between abstract algorithms and real-world performance, ultimately transforming chaos into order.